Good afternoon, everybody. I'm going to do a little recording here on Hess's law as another way to find enthalpy. To bear with me a little bit, I'm trying a new device for recording on SmartNotes and can't quite get my pen to be as thin as I would like, so we're going to have to deal with a little bit of a crayon here. So remember with Hess's law, what the idea is that we want to take these three equations. So we have equation 1, 2, and 3, and we want to manipulate them to look like the equation here, this final equation that we have for Hess's law. So it might be a situation where we can't actually measure the change of enthalpy of this particular equation, but we can do it with three other ones, add up their enthalpy values, and figure out the overall change in enthalpy for this reaction. So we want to make sure that we start at the beginning and that everything is in the forward reaction. So we have a synthesis reaction here. And when we are done, we want a synthesis reaction. If we had it in the opposite direction, then we would just change the sign. So here I can see my first one, I have 2 moles of carbon. So I look up here and I have 1 mole of carbon. They both are reactants, so that looks fine. So I'm going to have to multiply this equation by 2. And you can see I went and multiplied my enthalpy by that, because if I'm going to double the equation, I have double the amount of energy that's being released. So just like in math class, you can't just do multiply by one thing, you have to multiply all of it. So you can see I'm carrying that value of 2 and multiplying through the whole equation. So now I'm done with my carbon. Now I need to find 3 moles of hydrogen gas as a reactant. And if I evaluate this, I have 2 moles of hydrogen gas. It is a reactant. So if I go ahead and multiply by 3/2, that would give me 3 moles of hydrogen on the reactant side. So I'm going to multiply all of this by 3/2. And then I will get 3 moles of water here on the right-hand side. All right, now I need to look at my last one. You can see I have 1 mole of ethane, that's ethane there. And if I look at the given data, I can see that I have it as a reactant and I have 2 moles of it. So I am going to have to divide by 2 first to get 1 mole of it, and then I'm flipping the equation. So instead of being an exothermic reaction, it's going to be an endothermic reaction. So I'm flipping the reaction, so I flip the energy, flip the sign, and divide by 2. So then I will get 4 divided by 2 is 2 carbon dioxide, 2 carbon dioxide, and 6 divided by 2 is 3 water. And then I have 1 mole of ethane, and then 7/2 of oxygen. Now what I want to do is I want to add all of those together, and I want to make sure that I have canceled things out on both sides. So first I'm going to take a look one more time. Yes, I have 2 moles of carbon on the left-hand side. I have 3 moles of hydrogen as a reactant on the left, and I have 1 mole of ethane on the right. So everything else needs to be, make sure that it cancels out and do the work, because this is something that AP likes to do, is do some tricks in case you have to manipulate things within. This is not one of those, but I can see that I have 2 carbon on the left, 2 moles of carbon dioxide, 2 moles of carbon dioxide on the right. Easy to see that I have 3 waters and 3 waters. And then I got to do a little bit of math here. 2 plus 3/2, so 2 would be 4/2. So 4/2 plus 3/2 is 7/2. So I can see that my oxygen indeed cancels out. So all of that's going to give me my resulting equation that was given, that I wanted to find the overall enthalpy for. So here is my reacting equation. And if I do the same thing and add all of my delta H values up, I can see that this is going to give me an exothermic reaction releasing 86 kilojoules of energy, which is exothermic. So I would write my delta H is equal to 86 kilojoules being released. Okay, so what this does for us is we are now taking a look at that we've had a lot of ways of calculating enthalpy. So you need to really think about the different ways and what kind of information they give us. So jot somewhere down on the back page of your notes or whatever works for you. So for calculating delta H, some things you need to think about for calculating our enthalpy. The first one we did was with calorimetry. And with calorimetry, we know that Q is equal to mc delta T. And after or through our calculations, we need to think about, we want to be the system as chemists. And so positive or negative work that's done on the system has to be equal to the positive or negative work of the surroundings. And again, if one is positive, then the other is negative. And then that is going to be equal to the positive or negative endothermic or exothermic, the enthalpy of the system. So if you're given things like mass and change in temperature, you're going to do this. And then let's say you're not given any of that. You're giving the change in heat of formation of substances. Then we know that we can calculate the enthalpy by taking the summation of the change of formation of our products minus the summation of our change in enthalpy, the formation of our reactants. And keep in mind that if they are natural substances, the way that they are on a periodic chart, there is no heat of formation, and that is going to be 0. And then the last way that we just talked about was Hess's law, and that also will give us an overall value for our enthalpy of our reaction. All right, that's it. I hope you guys are doing well, and I will see you in quotes soon in class. Bye-bye.